last week we covered the counters and timers. And these are one of the interrupts. And what to do with the counter and timer is that sometimes you want to count the external events, such as, let's say you have a keyboard as an external device, and sometimes you want to count, say, how many click you want to have with the buttons. In that case, such kind of external event is coming into the processor, and sometimes you want to count. So we need a counter to do that. And another times, which is actually popular, is that sometimes you want to have an exact or precise delay. For example, I want to do some like LED flashing in 1 millisecond, every millisecond. In that case, someone has to count a millisecond. Okay? That's called the timers. So we run the timer inside the hardware processor, and that hardware will measure the 1 millisecond. You don't have to do it by yourself. So the hardware will help you and measuring the 1 millisecond and tell you, okay, it's been 1 millisecond now, so you can do like flashing, for example. So what to do with this is that there are 3 different ways. Let me review one by one. So in order to measure a certain delay, easiest way to do is to use a pure software technique. So since this is a software technique, this is nothing to do with any hardware. Any processor, any hardware, you can do the same way. Okay, you can use the same software routine. So in this case, what you do is that NOP is one of the operation doing nothing. Okay, no operation. So using this NOP, you can do a loop, as many loop as you like. Then let's say you do 1,000 NOPs, then you have 1,000 NOP delay. Actually, how much delay you have for each NOP? One NOP corresponds to 1 cycle of your hardware. So in this case, you have 1,000 NOPs, and how much time you have one NOP, it depends on your processor. Sometimes your processor runs very fast, then each NOP takes very short time. But for our 8051 processor, NOP takes 1 cycle, and 1 cycle, it's probably 1 microsecond or something. I think, I'm not sure, but that's not that short because our processor is pretty slow. So in that case, 1,000 NOP. But anyway, the delay here is based on NOP cycle. But NOP, how much time it takes in NOP depends on hardware. So what that basically means is if you want to have a 1 millisecond delay, then you need to calculate. Okay, what is the clock cycle of my processor? Maybe it's a 12 megahertz. Or sometimes if you use a fast processor, maybe the clock cycle maybe is 100 megahertz. In that case, 1 NOP is very short, right? Because this is very fast hardware. In that case, in order to measure 1 millisecond, if your NOP is very short, then you may want to run 10 maybe million NOPs, maybe, right? Or if you use a slow processor, maybe 1,000 NOP. So what I'm saying is that if you use this software technique, then it is very difficult to measure exact 1 millisecond. Because now, how long it takes depends on the hardware. If the hardware runs fast, then this one will be very quick. 1,000 NOP, looping 1,000 times, it's going to be very quick, right? Because the processor is very fast. But if you use a slow processor, then 1,000 NOPs takes a long time. So it depends on hardware. So this is not a good way, typically, right? This is a very easy way, but it's not accurate. Okay? So I just want to compare this way, this technique, with other technique. That's why I introduced this, but this is not a good way to measuring the delay. A better way to do it is that in order to measure 1 millisecond, now you are using hardware. So here's the what's happening. Let's see the hardware. I think there was a little bit confusion about these things. So we have 8051, our microprocessor. Right? In our microprocessor, inside here there are a lot of blocks, like ALU, you know, right? Arithmetic logic unit. This is where all of the calculations is done, like addition, subtraction, rotation, and all these things is done in here, ALU. So there's a block called ALU. And there are other parts like memory, registers, and things like that. And there is one part of the hardware which are dealing with interrupts. So maybe we can say interrupt block. So there is some hardware block which take care of the interrupts. Inside of this hardware, we have a registers called IE, IP. What is IE? Interrupt enable register, interrupt priority register. Okay, these registers belong to this block, interrupt block. Okay, again, I'm talking about hardware, right? There's another hardware called the timer. That's what we are talking about now, actually. So this is a separate hardware. We have a hardware called the timer. And we have another hardware called the serial port, serial communication. This is actually what I'm talking about today. This is last week, right? We talked about timer last week. So this is a separate hardware. And inside this timer hardware, we have other registers called the T-con, T-mode, timer control, timer mode. Okay? So these timer control, timer mode, these two registers belong to timer hardware. Okay? But interrupt enable, interrupt priority, these things belong to this. Now we're going to cover a little bit later today, but this serial communication block, this is another hardware. This hardware also has a register, S-con, serial control. Okay, we'll look at it in a minute. But this one has its own register also. So now, let's think about it. This is the interrupt we learned, right? And inside this register, we know that there are 5 different interrupt sources. Timer. There are actually 2 timers, right? Timer 0, timer 1. 0 and 1. And external interrupt, 0 and 1. And serial interrupt. So let's think about timer 0 as an example. Okay, timer 0. Now, inside here in interrupt block, you have to enable the global interrupt. And also you have to enable timer 0 interrupt. Right? Once you do this, in here, in this block, now then you are ready to get interrupt. Because you enable the interrupt. So now I'm ready to get interrupt. However, just setting these 2 bits, you are ready to get, but interrupt never happens. Why? This is what I'm saying as the telephone. Okay, remember the illustration. So this is like the electricity in our house. This is like a telephone. So when you enable these 2, it's basically the same as you buy a telephone and plug into the power outlet in your home, but no one calls me, so telephone never rings. Okay, I have a telephone here, so I'm ready to get a telephone. My telephone is ready, but no one calls me, so it never rings. That's the condition right now. Okay, you are ready to get an interrupt in here. But in order to actually get a timer interrupt, what you need to do is you also have to configure this hardware. So this is a timer hardware. Okay? How to configure is that you have to program this one and this one. And how to program it? That's what we discussed last week, right? Here, like this one, for example. This is an example. You have to program some value in T-con, timer control, or timer the mode registers, and also based on how much delay you want to measure, depend on that you want to program a initial value like this, right? Once you do all these things, tcon, tmod, th, tl, all these things, okay? Once you do all that, then now you configure these things, so you program the hardware timer, now you run the timer. Once you run the timer, then this timer will run. Let me go to here. That's what we're talking about now, right? So this is the global, this is not interrupt. This is the, let's say these two and these two are timer 0, okay? So you set some configuration in the tcon and tmod, and then you run the timer by setting this bit to 1. Okay, you first have to program some kind of mode setting like this, and also you have to configure the initial value into th and tl. Then I'm talking about this part, right? Timer part. You have to configure tcon and tmode, and also you want to program some write value into these registers, okay? And then once you program in write value, finally you're gonna set this bit to 1. Once you set this bit to 1, it's the same as like you power on this timer block. Then once you set that TR bit to 1, now this timer hardware runs. And when it runs, what happens is now the clock cycle comes in. Okay, you have a clock. Okay, the pulse train is coming in. Once you run it, now then switch is closed because you set it to 1. So when you set it to 1, now this switch is closed. Your pulse train is now coming to the hardware, the timer hardware. Therefore, that pulse train eventually comes into the timer. I mean, which timer you use, you have to program it before, right? You already have a program, which timer you use. Okay? So now when you run it, then your pulse train comes in here, and this is simply a counter. Every time you get a pulse, this one is incremented. Every time you get a pulse, it's incremented. Eventually, you get 1,000 pulses. Eventually, this is incremented, and then eventually what happened? This value, right, will overflow. At that time, whenever that value becomes all 0, then now you see this bit. Initially, this overflow bit was 0, but when you keep counting and that value, the timer value becomes 0, now you have overflow, this bit becomes 1. Okay, this bit becomes 1. So when this bit becomes 1, that's the time of exact 1 millisecond. Okay? Right? Initially it was a 0, but whenever you get 1,000 1,000 pulses, okay, then after 1,000 pulses, the timer will overflow. That time you see that this bit becomes 1. And once this bit becomes 1, okay, when the TF0 bit suddenly becomes 1, then that basically means the timer is now getting interrupt to the interrupt block. Okay, now the timer hardware will set the TF equal to 0, TF0 equal to 1, meaning that it's getting interrupt. So finally, now we enable the interrupt by setting these 2 bits, and we also has interrupt event. So therefore, now we actually get an interrupt to the software. Okay? So we need to have these 3 events. You have to set this one in order to get ready to get an interrupt. You also have to program the timer hardware such that timer runs, and when overflow happens, okay, when overflow happens here in the timer, it actually gets interrupt. It gets interrupt event. And when you have this event and you enable the interrupt block, then you get an interrupt. Software get an interrupt. Now suppose that let's say you program the timer. like this one, right? You configure the tcon, tmode, and initial value of all these things, and you set it to run, like setting this bit to 1. Then this hardware runs, okay? And when this hardware runs, every time you get an overflow, you have the value, this bit becomes 1, and this event occurs here. But as a mistake, let's say, you mistake, and then you didn't set this to 0. You didn't set these bits. You just set it. You just leave it as 0. Okay. Suppose that's the case. You correctly configure the timer hardware, but you forgot to set this interrupt block. In that case, what happened? Actually, interrupt event happens, but this interrupt block is not ready. Okay? So for software perspective, software point of view, interrupt never happens. This will be ignored by this block, right? This block will ignore this. And putting another way, you enable the interrupt block, but you forgot to program the timer. Okay? You didn't do anything on the timer. In that case, this block is ready to get interrupt, but actually event does not occur, right? Because you didn't configure the timer, so timer does not run. So never the timer interrupt never happens. So we are talking about two different hardware. The 2 weeks ago we talked about this hardware, interrupt block. Last week we talked about this hardware. But actually you need to program both all together. Okay? We learned the two different blocks, okay, separately, but you need to program all together. Only then you get an interrupt. And today what we're going to talk about is this one. It's the same thing. If you want to use serial port interrupt, in that case, again, you have to program the interrupt enable, global interrupt enable to 1. And also, you have to set serial port interrupt to 1. Okay? Once you do that, now you are ready to get a serial interrupt. But you are only ready. Nothing happens. In addition to this, you also have to program this block using this register. Okay? Using this register, you have to program this one. Once you program this block, hardware block by this register, then now this hardware start to run. Once this run, now in certain cases this one send the event to this block. Okay, only then now we have a serial interrupt. Okay, so that's how things work. So for the timer, as a review, as I said, that this is the bit to run the whole timer. Okay, if you set this to 0, then this switch is open. If this switch is open, here's a pulse train, but pulse train never comes to timer. So timer is not doing anything, right? So you need to make this 1, but you want to set this bit at the last stage of configuration, because you want to program the initial value first. What is the initial value? This value, right? How to set the initial value? Let me review it. Let's say we are using this timer. This is a 13-bit timer. Okay, so 13-bit. We have a 13-bit like this, and maximum value you can have with this 13-bit is 2 to the 13 minus 1. So that's the case of 1, 1, 1, 1, all 1. 13 ones. 13 ones. We have a 13 ones. That's the 2 to the power 13 minus 1. That's the maximum value we can have. Okay? That's the maximum. And if you have one more, then the remaining value here in this timer becomes 0. and now we have a timer overflow. So now we have a TF0 becomes 1 at that time. Right? That's the time we want to detect. Okay, we simply the detection is like we are watching. We are simply watching this block. Once you run it, setting 1, and once you run the timer, then what you need to do is you are watching this bit, TF bit. Initially it's 0, but we just watch this, and when this becomes 1, that's the time you want to stop. You want to get, right? That's the time that you actually get exact time delay, 1 millisecond, for example. So you're just simply watching this bit. And when this happens after a certain cycle. So what you want, for example, is that I want to count 1,000 cycles as an example. Right? Sometimes maybe you want to count 2,000 cycles, depends on you. So suppose that I want to count 1,000 cycles, then what you want to program here is that as an initial value is that you want to program this value as an initial value here, right? Remember that? This value has to be programmed here as an initial value. So you need to program those values here first. First, you want to calculate that value and get this value and program it here. Okay? First, you need to program it here as the initial value, and then you run it. Okay? Because once you run it, then it's running already. You cannot write the initial value. It's no longer initial value because it's already running. So before you run, you need to program the initial value first. Okay? And also you need to program these things, T-mode and T-con. You program all these things. Okay? And then finally you run it, then timer runs. And you watch this until this becomes 1. And every time this becomes 1, then there are 2 ways. That's what I'm saying here. There are 2 ways. One way is to do software polling. What that means is you program the timer like this, T-con, T-mode, and TH0, TL0. This is the initial value. You program it like this. Then timer runs. And for the software, what you need to do is you are just watching this. We'll just watch it until this becomes 1. But in that case, what you need to do is watch. You cannot do anything else. You have to watch it. Or maybe if you want to do something else, then maybe you are doing something else, but you need to keep watching. Every time, like every 10 milliseconds, you have to watch it. And you do something, watch it until it becomes 0. So that's not very good, right? Because you have to watch it. So but you can do it if you want. That's the software polling. What is a polling? Polling is like do something periodically. That's polling. So you run the actual 1 millisecond delay is measured by the hardware because you program the hardware. Hardware will run. Hardware will measure 1 millisecond. Okay? And whenever the hardware finished measuring 1 millisecond, hardware will program this one to 1. That's the job of the hardware. But for software, what you need to do is you have to look at this until this becomes 1. That's your job as a software. So that's one way to do it, software polling. But in this case, as I said, you have to watch TF0. So that's not really good. So better way is the last one, pure hardware technique. In this case, what happened is that you run the hardware same way. Okay? Hardware programming the timer. This timer, you can run the same way. Because what we want is to measure the 1 millisecond. So you program it that way. And this hardware will run to measure 1 millisecond. And as soon as whenever this overflow happens, TF0 bit becomes 1. Same as before. But in this pure hardware technique, difference is that now you program this block. In the earlier software polling, you only program this timer and you didn't use interrupt. That's why you didn't use interrupt. That's why you have to watch this TF0 until this becomes 1. Because I don't know when this becomes 1, so I have to watch it until the hardware finished 1 millisecond and program this to 1. I want to detect that. That's software polling. But in pure hardware technique, what you do is that you enable this block also. You are using 2 hardware blocks. So once you do that, right, then what happens is when the timer block finishes the 1 millisecond measurement, then TF0 bit becomes 1. Then automatically this 1 means that the interrupt event occurs here. And if you enable these 2 bits, now my software will get interrupt. So that's the difference. So in that case, as a software, I don't have to watch this. I can forget, and I can do my own work, some other work. Okay? Forget this, and once I program all this, then I do my own work. And whenever the hardware measured 1 millisecond, then hardware gives me interrupt. Okay? When I get an interrupt, that means it's 1 millisecond. So I don't have to watch this. So it's more efficient. It's a better way, actually. It's the best way, in fact. Okay, that's what we talked about here so far. The pure hardware technique is also use interrupt. So look at here. Let's go back to pure the software polling technique. In software polling here, you are using hardware timer. So therefore, you see these lines. Tcon, Tmode, Th. You are programming all these hardware timers. But you never touch the interrupt hardware block. However, if you go to the next one, which is pure hardware technique, your same way you are programming the timers, same, Tcon, Tmode, Th, Tl. You are using the hardware timer, and also you are using hardware interrupt block. See the interrupt enable? Okay? We are using interrupt block also. Okay? We are using interrupt and timer hardware. So in this case, hardware will do everything. Okay, hardware will do everything. Software, forget everything. You know, I don't have to worry about anything. Whenever the 1 millisecond happens, then I'll get an interrupt. Okay, that's very efficient, right? That way I can do my own work. So these are the steps to do in order to make a timers work. So first, you need to configure the T-mode registers. T-mode is here. Okay. We have 2 different timers, right? Timer 0, you need these 4 bits. Timer 1, you need the other 4 bits. Okay, we have 2. So based on that, you can program the T-mode. And also, you need to program TH0, TL0. Why do we need this? Because this is going to be the initial value of your timer. So you need to program the timer. Once you program the T-mode and initial value, now we are ready to run the timer, so you run it. So this is the instruction, you run the timer. Set B means you are setting only this bit, 1 bit. So this is 1 bit, PR0. Okay, so you run the timer like this. Once you do this, now the timer runs. Okay? Once the timer runs, actually in this case, we didn't use interrupt yet. Right? I didn't program any interrupt. So in that case, what do you need to do? Since I didn't use the interrupt, what you need to do is I have to watch this bit, TF0, until this becomes 1. Okay? That's one way. The way I said as a software polling. But what is a better way? Better way is to use interrupt. That's a better way. So to use the interrupt, what we need to do is that you will program this timer like this, but before configuring timer like this, okay, up here, you want to enable the timer first. You want to enable the timer interrupt, and then now you program the timer and run the timer. That's a better way. Once you enable the timer interrupt first, and run the timer. Then now, whenever the timer interrupt happens, then you will get the timer. Software will get the timer interrupt. Then you jump to the timer interrupt service routine, and you do whatever you want in 1 millisecond inside the interrupt service routine. Okay, that's what we do. And sometimes you may need to clear the overflow. Okay, what this means is this one. Let's say, coming back here, let's say timer runs, and let's say we want to measure 1 millisecond. So hardware timer runs and measured 1 millisecond, and overflow happens, so this becomes 1. Now, for software perspective, what we need to do? Since we know that, okay, now it's 1 millisecond, that's why hardware gives me interrupt. So maybe I want to do my own work. Let's say I want to do LED flashing in 1 millisecond. Then whenever this becomes 1, I want to do that one, right? Flashing. And then what do you need to do also? You also need to make sure that you have to clear this bit. Make this 0. Why do you need to make this 0? Because you want to get the next interrupt. If you leave this to 1, then next time hardware program to 1, then it's still 1, right? So you cannot see the difference. So you need to make sure that you clear this bit to 0. Hardware will program to 1, and software will clear to 0. Okay, hardware will make it 1, software make it 0. And later the hardware makes it 1, and I make it 0. And hardware later 1, 0. Something like this. Okay, that's what you need to do. That's what you're saying here. Clear TR0 and clear TF0. Okay, sometimes you need to clear those things if you need. Okay, that's some instruction about the timer and how to use it with interrupt. Okay, today what we're going to talk about is serial data communications. That's this block, serial communications, like this one. So let's look at some brief introduction about the serial communications. What is a serial communications, by the way? But what is the others then? Is there any parallel data communications? I don't know, how many of you remember a parallel port in the PC? Does anyone remember? Have you seen the parallel port? Okay, these days I think the PC, the computer probably doesn't have a parallel port. But maybe some of you remember that you buy a printer, right? These days, most likely a printer has a USB port, USB connection. But going back like 10 years ago, pretty much every printer had the parallel port connection. Remember? Some of you looked at it, right? Let me draw it here. It looked like long, and there are a lot of pins. That's a parallel port. Okay, some printer, actually most of the printer in 10 years ago had this interface, and also your computer has this interface, okay, in order to connect to the printer. That was the interface most popular for printer at that time. So this is called a parallel interface, whereas this one is a serial interface. So what's the difference? Simply speaking, serial interface or serial communication is like you send the data in serial fashion. What does it mean? Let me draw it here. Serial parallel communication. Serial communication. What this means is in serial communications, you have one line, one or two, something like this, and the data you transmit is going serial, like all of the bits, 0, 1, 1, 0, 0, 0, 1, 1, something like this. They go all in one line. Okay, This bit goes first, and then this bit, and then this bit. They're standing on one line, okay? One after another. They go all in serial. Whereas in parallel connection, we have a lot of connections like this. So these bits go in parallel. 0 over here, 1 over here, 1, 0, 0, 0, 1, 1. So in this case, we have 8 lines, 8 different lines. So all of the 8 bits can go all together. Think about the road, okay? It's something like I don't know, is it? I'm not good at drawing, but let's say this is a car going. Okay, there's another car like this. It's coming down. So this is one lane. So all of the cars has to go one after another because we have only one lane. That's a serial communication, right? It's all going one lane. But this parallel communication is like we have many lanes like this, like highway. So you can actually have many cars go in parallel. Okay? All these different bits can go at the same time in parallel because we have multiple lanes. That's a parallel communications. So it sounds like this is better, right? Sounds like this is better because in this case, the many bits can go all together at the same time. Going back to 10 years ago, again, 10 years ago, this parallel interface was used for printers, as I said. And at that time, there was another interface like this, small one. Okay, this is called RS-232. This is the name of the interface used in PC. And I don't think we have this anymore in the PC. This is old-fashioned, old interface. And this one is called it's a long one. I think this is a RS-481 or something like this. I forgot the number, but this is a parallel interface, typically for printers. This is an interface typically for mouse or keyboard. Okay? If you have an old computer, then maybe you can look at the back side of the computer. You will see this kind of interface. This one, since we have a parallel communication, parallel link, many links, this one is typically for higher data rate. You can transmit higher data rate. But this is a serial communication, so all of them has to go on one line. So therefore, this is a low data rate. Slow, right? This is faster, right? Just like common sense. So this is a faster, this is a slower. But in terms of data rate, this is faster, this is higher data rate, lower data rate. But compared to, let's compare these two interfaces in terms of, let's say, cost and convenience. This is much better because in this case you have a lot of lanes, a lot of link or wire, let's say. There are a lot of wires. So it's actually more expensive and it's more complex and it's more everything. In this case, it's very simple. That's why, what does a USB stand for? USB stand for S means a serial, right? This is a serial communication, like this. This is like a USB. USB is like this. Look at the USB interface. You only have 4 pins, right? Serial USB is not like this. So why this is a higher data rate, and why everyone is now using serial communication? Why not use this one? This seems to be better. Because this is much easier to use. It's better, actually. in many ways. So this is why the serial communication is much more popular these days. Parallel communication, it's not that popular. Think about all the interfaces, like USB. And does someone know the FireWire? There's another interface called the FireWire. FireWire, or you call that the IEEE 1394. That's another name of FireWire. That's the interface used in Apple PC long back. Okay, so all of those things are now in serial communications. So serial communication is actually more popular, and we probably want to know something about this. So in serial communications, we can say there are two ways. One is a synchronous serial communication. The other is asynchronous. In the synchronous serial communication, we have a 3-wire, okay, 3 lines. One is called a clock, another is a data, and the third one is ground. When you learn the digital circuits, for every digital circuit, you need to have a ground, right? For every digital circuit. Otherwise, you need to have a ground. Only that way now we can say whatever transmit over data pin is 1 or 0. Okay? Easy way to see it is that when you transmit 5 volts, that is 1, right? Typically, that's how we see it. 5 volts, 1, and 0 volts, 0. Right? That's typically what we see. But how do you, let's say you transmit a certain voltage, how do you know that's 0 or 5 volts? You need to have a reference. This is a reference. Let's say we have a building like this. We are now in second floor, right? This is second floor. So how do you know this is second floor? Because look at the ground. Ground is right there, right? That's the ground, and that's the first floor. This is why we are in the second floor. Suppose that my ground is up here. In that case, we are in the first floor, right? If the ground is up there, then we are maybe in the basement. So you need to have a reference, like a ground. For voltage, the same thing. If you have 5 volts, that means nothing. Only when you have a ground of 0 volts, then I have in 5 volts, so I'm in 1. Okay? So you need to have a reference. Only that way I can see that, okay, my data is 1 or 0. So that way you need to have ground and you need to have data. You need these two. But in this case, it says asynchronous. So therefore, you need to have a clock. So here's how things work. So you have a transmitter here. You have a receiver. Now we have a clock pin. We have data. Let's say we have data here. Of course, we have a ground, but let's skip the ground pin. So we have a clock like this. So how things work is that over this clock pin, you are sending clock. Like this. That's what it transmits over this clock pin. For data pin, now you are transmitting data. Let's say I want to transmit 1, 1, minus 1, let me take it 1 or 0, 1, 1, 0, 1. Let's say I want to transmit 1, 1, 0, 1. In that case, how I do it is that I make it 1, 1, 0, 1. That's what I'm going to transmit over this pin. Why is that? Because I want to make it aligned. Okay? So this is 1, and that's within this clock. And the next clock, I transmit 1. Next clock, I transmit 0. On next clock, I want to transmit 1. So it's asynchronous because my data transmission, my data is synchronized. Synchronized means aligned in time, right? It's aligned in time with my clock. Okay? That's how things work in synchronous communication. Then let's talk about asynchronous. Okay, when you look at these two, okay, then now you can easily understand. So let's look at asynchronous communication. In asynchronous, we have no clock. We don't have this clock. Okay, we only have data and ground. That's it. Okay, now then, what that means is we have no clock. Like this. We have nothing on the clock. We only have data. Like this. Then how can you do communication? In this case, what you can do maybe is that you can just transmit 1101. Maybe you can try that. So same way, let's try that. 1, 1, 0. Let's do it this way. 1101, 1. Okay, let me transmit 101011. Okay, I'll tell you why I use this example. Okay, so 1, 101011, 1. So if the transmitter transmit 101011, 101011, in that case, maybe receiver can detect this because it's 1 and suddenly it drops to, we have a ground, right? So we know this is a 0 volt and this is a 5 volts. So receiver is receiving 5 volts and here at this time signal drops to 0, ground, 0 volt, and it stays with the 0 volt with this much of time and then comes back to 5 volts and a little bit later again going back to 0. So it's going up and down, up and down, up and down. So now the receiver may be able to get plus 1, minus 1, plus 1, 0, plus 1, 0. Maybe you can do it in this case. This is like a happy case, right? This is like a good case. But let's say, as another example, let me say I want to transmit 111001. In this case, what happens is I have a 1 and still 1, and now it's dropped to 0, and again 0, 1. In this case, it's not like up, down, up, down. It's like stays to 1 for a long time, and down to 0, stay for a certain time, and going up and stay. Something like this, right? In that case, receiver doesn't know. Receiver doesn't know what is the size of your sample. Each one is one sample. This one, right? Receiver never knows the sample duration. Without knowing the sample duration, it cannot detect. Okay? You need to know what is this is a sample duration. You need to know the sample duration. But there's no way to find out the sample duration because this one does not going back and up and down, up and down. Do you see what I'm saying? So here's what I'm saying. Let's say this transmitter transmits 110011. In that case, and let's say one sample duration, let's say is 1 microsecond. I'm talking about just example. In that case, 1, 1, 0, 0, 1, 1. This is what transmitter is transmitting. So 1 millisecond here, 1, another 1 millisecond here, another 1, 0, 0, 1, 1. So total is 6 microsecond. That's what we transmit. However, from the receiver perspective, receiver doesn't know anything about this. So receiver only detects the edge, drop or up, edge. So this is the edge, one edge. There's another edge. So in this case, receiver may be thinking that, oh, looks like this is the just symbol 1. Looks like this whole thing is symbol 0, and this whole thing is maybe sample 1. So looks like this guy is transmitting 101, and each sample is 2 microseconds. Maybe this guy thinks that way, right? In fact, this guy is transmitting 1, 1, 0, 0, 1, 1, like this. But these guys think that, okay, 1, 0, 1, and 1 is like 2 microseconds, not 1 microsecond. So this is wrong. But this can happen. If you have a clock, then there's no misunderstanding like this, right? Because if we have a clock, then we're going to have a clock in every microsecond, like this. So we know that based on this clock, we know that this is actually 2 samples. These are actually 2 samples. We can easily see it because there's a clock. But if there's no clock, like this asynchronous case, then you can never see that. So now we have a problem in asynchronous case. In fact, in USB, you know USB is asynchronous. Okay? USB, the popular interface, USB is like this, asynchronous. Then how does it work? How can you make it work in asynchronous? Okay? That's what we're going to talk about in actually next slide. So let's look at it. But before that, okay, before talk about the details of asynchronous, going back to synchronous communication, let's briefly check one thing. In 8051 in our microprocessor, okay, there are 4 different serial communication mode. In fact, there are a lot of 4 in 8051 processor. We have if you look at the timer, okay, we have 4 different mode in timer, right? We have 4 different timer mode. In serial communication, again, we have 4 different mode in communication. 4 different serial communication mode. And mode 0, the first mode 0, is actually synchronous communication. And all the other 3 mode 1, 2, 3, all these 3 different other modes are asynchronous. And mode 0 is synchronous communications. And this is how the 8051 works in mode 0. In 8051, we have pins called RxD and TxD right here. Okay, this is our chip. We have a RxD pin and TxD pin. Using these 2 pins, RxD and TxD, now you can do it this way. We have RxD and TxD pin, and you are going to connect these 2 pins with other external receiver. Okay, an external receiver, and using this TxD pin, you are transmitting clock, like this one. And using this RxD pin, you can transmit the data. And of course, you have a ground in somewhere else, right? Ground is always there. Ground is always like here, right? You always have ground. But over this pin, you can transmit clock. Over this pin, you can transmit data. Then it's actually same as this one now, right? We are now in the same way. We have a clock and we have data over here. So now you can do this transmission, synchronous transmission with the 8051. So this is one way to use it. Right here, okay, look at this slide. It shows you 4 different serial communication mode. Mode 0, mode 1, mode 2, mode 3. And how to configure the mode, okay, mode 0 or mode 1, 2, 3 is configured by these 2 bits. We have a register called SCON. That's the register I mentioned earlier, right? SCON. Okay, this register is inside the serial communication hardware. Okay, inside the serial communication hardware, we have this register, and this register has 8 bits like this. And the first 2 bits, MSB, and the second, the first bit, this bit, SM0, SM1, these 2 bits indicate which mode you want to use. If you have a 0, 0 for these 2, that base means that I'm going to use mode 0. Okay, if you set it like 0, 1, like this, 0, 1. Then what that means is I want to use my serial communication with a mode 1. Okay, so this table shows you the difference of each mode. As you see here, mode 0 is only synchronous, and mode 1, 2, 3, they are all asynchronous communication. Okay, I'll tell you details about these others. So going back here, now another thing we want to remember is that we talked about inside the 8051, and we said that we have a serial communication hardware, right? Remember that inside the 8051, the processor, okay, inside the processor, we have the serial communication hardware block. And in this hardware block, we have a register called SCON. We have another register inside this hardware. We have another register called SBUF. That's another hardware, another register inside this hardware, SBUF. SCON, as the name says, SCON means the control register, serial port control. Okay, serial control. So this register is to control or configure the serial port, whereas this SBUF is another register only to use as a buffer. What is a buffer? Buffer is simply memory. Okay? This register is not to control, not to do anything. This is just to buffer. And this is how hardware looks like. So we have a TX and RXD. These are the pins that I mentioned earlier, right? Going back here, these pins, RXD, TXD. This is a pin, and we have two different pins. Basically, the RXD means a receiver, right? TX means a transmitter, basically, right? So these two pins, okay, each of these pins is connected with some other hardware. This is the inside the serial communication hardware. This whole thing is inside this hardware, okay? Serial communication hardware, okay? Inside that hardware, we have SBUF, but in fact, the SBUF is two of them. One SBUF here, another SBUF here, okay? In fact, there are two. But this SBUF is read-only for the software, for us, okay? We are using this processor. So for us, this is read-only. Whereas this SBUF is write-only. Generally, right? Generally, when you look at a certain memory, then typically you can write and also read. Generally, right? So that's like a read-write. That's a normal case. But in this case, this SBUF is read-only, and this one is write-only, which means that in this SBUF, you cannot write. You cannot write because you can only read. Like ROM, right? What is ROM? Read-only memory. That means someone else is writing there. I can just read only. Same here. I cannot write, but I can only read. Then who is writing? I'm only reading. Okay? I can only read. Then someone else is gonna writing something, right? So who's gonna write? This one, right? We have RXD here. For us, it's a receiver, receiving pin. So which means someone else is transmitting. Okay? Someone else is transmitting some information, and that information is received over here. And that received information is now going to there. So someone else out there, they are transmitting the value, and that value is coming in here, and it's automatically going to SBUF. I cannot write. I can only read. Look at this one, right? Look at this one. Actually, not this one, but okay. Here's a. we have 8051 processor, our processor. We have a TXD and RXD. So we have RXD pin here. And this RXD is connected with another transmitter. Maybe you can simply say that, okay, you in your lab, right? You have a 8051 board, and you connect this 8051 board with a PC, right? You have a PC. Okay, this is like a PC, for example. This is your board. Okay. Sometimes in your PC, maybe you can transmit some command. And that command go into here, go into the board, right? That's what I'm talking about here. So this one, it can be PC or it can be anything. But this guy is transmitting some information, like alphabets, for example, A, B, C, something like this, right? It's transmitting these kind of data. And this data is going here. And 8051 receives this, and this one automatically going into SBUF, like this. Once this is done, now then for us, we are reading it out. Okay, we read it out. So this guy is transmitting A, B, C, D. So when this guy transmitting A, now it goes into here. We have A. Now my software, here is the hardware. I have a software, and my software read this value out. Read it out, and read it out basically means like this. You can do like this. What is this? This basically means that you are copying the value in SBUF into A. That's what I'm saying is to read it out. Okay? So you copy the value inside here, A in this case, you read it and copy into A, accumulator. So A, this is accumulator, okay? Accumulator, now I have a value A, because A was in SBUF. Okay, when you do this value is now copied. Then a little bit later, let's say this guy is now transmitting next data, B. Then again, this one is updated with B. Then what you need to do again? You want to read the value out. If you don't read it, then a little bit later it will transmit C. You're going to overwrite the C, so you'll lose it. Right? Every time you have a data, it's overwritten. So you need to read it every time. This is what I'm talking about. That's the buffer to contain A, B, and those A is coming from PC, coming from external device. And we receive it, A, B, things like that, and that goes into this buffer, and I need to read only. I need to read it. Similarly, sometimes I want to transmit. This is the case of receiving. Okay, someone else is transmitting, I'm going to receive it. But sometimes I want to transmit. When you transmit, you are using this path. And this one is again the same name, SBUF, but this guy is only for write. Because when you transmit, you're going to write. So what that means is, whenever, let's say you want to transmit C, okay, letter C, then what you need to do is that you're going to write value into here. Then the hardware will transmit. Okay? You don't have to do anything. For software, I'm not doing anything. Okay? Let's see. I have another SBUF. This SBUF is for write only. I'm talking about now this one. Okay? I'm talking about this one. So if I want to transmit something, let's say I want to transmit C, then what do you need to do in software? Software, just simply write C into here. Okay, just simply write it here, C. Then the hardware, this serial communication hardware automatically take it and transmit. Okay? So software, you don't have to do anything, just write the value into C. So if you want to transmit some value, write it here. That's it. Then the hardware will transmit. If you want to receive something, then someone, maybe PC, has to transmit the value. Okay? So for example, this PC is transmitting letter B. Okay? And then we receive this letter B. Whenever we receive this letter B, that B goes into this buff, S buff, and this S buff is read only. So once we receive it, then for software perspective, we can just go there and read it. So I'm talking about only software. Okay? What I'm explaining here is a hardware. I'm just telling you how the hardware works. But from the software perspective, it's very simple. If we receive something, then the letter we received is here, already here. Hardware will do all that. So for software, just simply read it. It's something like this. Okay. Sounds like it's complex, but let's say I have two boxes, like this one, right? This box. I have two small boxes like this. And one box is called read-only SBUF. Another box is called write-only SBUF. I have two boxes, like these two. Okay? And let's say I have two boxes in my desk. And if I want to send a letter to my friend, okay, my friend is somewhere far, maybe in another building. So if I want to transmit, if I want to send my letter to my friend, then what I need to do is that I write the letter, of course. I have a letter to transmit, letter to send. And my letter, I'm going to put this box, okay? My box is right here. SBUF write-only box is right here. And if I want to send the letter to him, then what I need to do is I put the letter here in this box. Then someone else is coming here and take it and deliver to the friend. I don't have to go to my friend and deliver. What I need to do is just put it in my box. Then it's gone. That's what I'm saying.
That is divided 4 bit.
That is divided what?
4 bit.
No. It's 8-bit. This is 8-bit. This is 8-bit. Okay, I'll tell you what that means. This is actually same one, same register. These two, typically, you know that each register has a different address, right? Each register has a different address. But these two actually have a same address, 99H. It's the same address. Okay, for the same address. Okay, the way I'm talking about the two boxes is to help you to understand. But in fact, in hardware, it's basically the same address. You don't need a two different address. Why is that? Because this is only for read. This is only for write. So somehow you can put this together. It's one, basically. But anyway, just to help you to understand, maybe it's easier to think that these are two different boxes. If I want to send a letter to my friend, then what I need to do is that I can put my letter into this box. Okay? Then I don't have to worry about it. Someone else come here and take it and deliver to my friend. And let's say if I receive a letter, right? Then what I need to do? Again, someone else is delivering the letter and put it into my box. Then what I need to do? I just take it from my box. Then that's the letter for me. Someone else is sending a letter to me. That's already delivered in my box here. So I just read it. If I want to send it, I just simply put it. That's what you need to do. That's all you need to do in software.
Why is shift register in there?
This shift register, okay, so this one is actually serial communications. right? So you have a serial communication. So you have a bits, all the bits are on one line, one bit after another bit, after another bit. So those bits, all serially coming in, those goes into the shift register. You know the shift register? We have a shift register here, so that this one actually is related to other mode. Not always used, but other mode. We cannot, I think I don't have it here, probably next week, but there's a mode that you use a shift register. Typically, right now it's simple. Simply you can think that whenever you receive some bits, all the bits are coming in sequential way. One bit, and then the next bit, and then next bit. Right? That's all you do. So all the bits go into SBUF. Now we can simply think that way. Okay? All of those bits, 8 bits actually. This is 8-bit. All those 8 bits coming in, that goes into SBUF. So for us, what we need to do is simply read it from here. And if you want to transmit 8 bits, what you need to do is that write those 8 bits into here, then it's gone. That's the serial communication. So what you need to remember is these things. SBUF. So this is where you actually buffer your data. Okay, serial communication is to do a communication. So you have some data to transmit, and you have some data to receive. So data, actual data, goes in here. This is to control this block. Okay, this SCON is to control this block. Like this, right? All these bits are not data, right? Each of these bits are control bits. We also need to know the function of each bit. Let's look at briefly. The SM0, SM1, these two bits are used to select the mode, as you can see here, right? So depending on how you configure for these two bits, you are selecting one of these bits, one of the modes. SM2, this is not used. This is for future use, but right now we are not using, so forget this one. REN, that's receive enable. What is receive enable? This pin is the same as enable the receive. So that pin, REN, is right here, REN. Bit is something like this. So if you set this one to 0, REN bit is 0, that means our receive is disabled. If we have a disabled receiver, then what that means is, let's say your PC is transmitting letter B, but our receiver is disabled. So therefore, this B is ignored here. It's dropped here because this is disabled. So if you want to receive letter or receive some data, then you have to enable it. Okay? Only when you enable it, now whenever you have a B, whenever you receive B, this B goes into the memory, SBUF. Okay, now you have to enable the receiver. So this pin is like a switch, right? Switch on, switch off. Only for the receive part. Okay, receive part. Transmit part, you don't need enable, right? To transmit part, you don't need the switch. Why? If you don't want to transmit, then you don't write anything, right? Only when you transmit, you are writing. So you don't need a switch. Okay? But in receiver, you need a switch because sometimes you don't want to receive, but someone is transmitting to you. I don't want to receive it, but someone is transmitting, right? In that case, I want to disable it. So that way you can disable. This one, you can control it. You are transmitting only when you want to transmit. But this one, you cannot control because someone else is transmitting to you. So that's why you need the enabled bit for receiver. TB8, RB8, this one, okay, I'm going to talk about next slide. So we have a TIRI. I means interrupt. Now we have an interrupt. Okay? This serial communication can be used with interrupt. Okay? This can be used with interrupt. What that means is you can use this serial communication without interrupt. Remember the timer interrupt. Okay? Mentioned earlier. We have a timer hardware block. We also have a separate interrupt hardware block. Right? So sometimes if you want, you can use the hardware interrupt, the timer hardware, and also you can use interrupt hardware. Okay, all together. That's probably the best way. But if you want, still you can use like you only use the hardware timer, but I'm not using interrupt. You can still do that. Remember, we talked about that, right? In that case, how do you use? You are going to do polling. You can do the same way here. You can use the serial communication hardware with interrupt or without interrupt. You can do the same way. But if you want to, but let's in timer hardware, right? Whenever the timer hardware overflows, now what happens? You have a TF bit to 1. Remember that? In timer hardware, right? Whenever the interrupt event happens, let's go back to timer. Whenever the timer expires, okay, timer interrupt, a timer expires and timer event occurs, you have this bit to 1, right? This becomes 1. Same way, in serial communications, whenever we have receive interrupt event happens, you get this value to 1. Whenever we have a transmit interrupt happens, we have this bit to 1. So in serial communication, we have 2 interrupts inside serial communication. We have transmit interrupt, we have a receiver interrupt. Whenever the transmit event and receive event happens, you have 1. And also 1 here. But these 2 are independent. Does it sound complex? Okay, later when you use this, then you'll understand it. This is not that complex. Okay, nothing complex. So this bit, it becomes 1 only when you have a transmit is done. So here's the thing. Okay, let me simply explain here. So going back to this figure, okay, here's what's happening. Going back to my previous example, let's say I want to transmit A, B, C, D from PC to my processor. Okay? In that case, in my PC, I'm transmitting A first. Okay? Assuming that receiver is enabled. When I from the PC, let's say I transmit A, then A goes into here. Okay? Because I transmit A. And then my software has to read it. And then once this is read it out, then now you can transmit B. And B goes into here now. And software again read B. That's a normal sequence. But now the thing is that let's say PC is transmitting A first. And that A goes into here. From the PC, I want to transmit B because that's the next letter. But how does PC know that software already read it? Software simply just read it here. And from PC, I'm just transmitting A, B, C, D. Okay? This can happen. Let's say PC is transmitting A, and A goes in here, and software is doing busy with something else. Okay? My software was doing something else, so I'm busy. And software doing something else. In the meantime, now the PC is transmitting B. And now the A is gone because now we have a new letter B here. So in that case, the software didn't read it yet. But PC doesn't know. PC never knows if the software already read it or not. Okay? So the PC just simply send A, a little bit later B, a a little bit later C, a little bit later D, right? It doesn't know, it never knows that the letter is already read by software or not, right? And another thing is that, let's think about the transmitter side. Software, let's say my software, if I want to transmit letter, let's say in this case, I want to transmit ABC. So if I want to transmit ABC, software, what I want to do is that I just write the A value here. Whenever I write value A, then now the hardware will take this and transmit. But this one takes certain time, right? Because A is actually 8-bit, like 0, 1, 0, 1, 1, 1, 1, 1, something like this. Okay, this is just an example. Whenever you write A value into SBUF, it goes into ASCII mode. You know ASCII? ASCII is the ASCII type, right? So A is now converted into 8 bits, and these 8 bits has to go one by one. 0 first, 1, 1, another 1, something like this, right? That's what happened because this is a serial communication. So all these 8 bits has to go one after another. They have to go all 1, 9, 1 bit first, 1 bit, okay? 1 bit by 1 bit. So it takes time. It takes certain time to finish all transmission. But let's say software doesn't know. Software never knows that if all these 8 bits is already transmitted or not. So think about this way. Let's say the software wants to transmit this one very fast. I want to transmit like ABC, very fast. So what you can do is that you write A value A, and immediately later you write the value B. If you do that, then what happens is that when you write the value A here, now the hardware will take this one and convert it to ASCII and transmitting, but I didn't finish it yet. Maybe I transmit this one and this one and this one and this one. I was transmitting somewhere here, okay? I'm in the middle of transmission, but suddenly software write it into B. In that case, all this becomes garbage now, right? Because suddenly these 8 bits in here is now changed. So the best case is that software write A and hardware finish transmitting A. And then now the software write the B. That's the best case. But software doesn't know. Software has no idea that hardware already finished the transmission or not. Okay? So we have some problem like this. Software, what I'm doing is just to take the software, what I'm doing is I just write the value into A. Write the value into SBUF. That's all I do. And hardware, what it does is that take the value from SBUF and transmit one by one, 1 bit by 1 bit. But this hardware never talk to the software. So if the software write the value too fast, then the hardware didn't finish it. I was transmitting A, but in the middle of the transmission, software writing another value. So my transmission is messed up. In order to avoid such kind of case, that's why we need interrupt. So this interrupt, transmit interrupt and receive interrupt, is like a communication between the hardware and software. So what I do is that something like this. Software, let's say I want to write ABC as fast as I can. Then I write the A value into SBUF. Okay? And wait. Write A and wait. And hardware will take A and transmit A 1 bit by 1 bit. And after hardware finishes transmitting A, now the hardware gives the interrupt to the software. Okay, I finish my transmission of A. Then software receives that interrupt. Okay, now then, A is finished. Hardware finished the transmission of A. Now it's time to write next letter. So let's write B. Okay? Same way the hardware finished the B, send the interrupt. That's how this interrupt works. Okay? Same way in the receiver. In receiver, what happened is, now the hardware, this is hardware write the value into here, and software simply read it out. So same way, hardware write the value. Whenever the hardware receives this value A from the PC, and hardware write this value into this SBUF, then send the software interrupt. Now the software waiting in interrupt, and whenever the software receives the interrupt, now what that means is, okay, something is delivered. I have some mail. Okay, when you send email, or maybe in your cell phone, right? Whenever your friend is sending you a text message, then you have some music, or you have some vibrating, or some clicking message or something, right? Why do you have that? Because the cell phone is now telling you, okay, someone is sending you a message. Same here. Whenever the hardware receives some value, then hardware write that value into SBUF, and then send the interrupt to the software. Now the software is waiting. And whenever it gets interrupt, now then go there and read it out. Okay? Again, then hardware receives the next letter, then write it into SBUF and send the interrupt to the software. Again, the software, whenever you receive the interrupt, then go there and read it. It's like a communication between hardware and software. That's why we need interrupt, like this, right? So we have a lot of mode like this. Okay, but let's cover this next week.